Okay, well, thank you very much for coming out on a Monday night. Hope you had a good weekend. My Saturday was 38 hours long, so it's good to be here. That's working, we're all working, wonderful. I'm probably loud enough, I don't need a microphone, but I'll stay roughly near it anyway. Hopefully at some point during this talk, my body clock ends on the coast of California somewhere. If I fall asleep, you'll just have to buy the book. So our topic tonight is the fine-tuning of the universe for life. So let me start with a gratuitous astronomical picture. We're going to be talking about the universe and the way it is, and in particular using our understanding of why it is the way it is to then think about the way that it could have been. So other ways that the universe could have been. And some pretty interesting stuff comes up. Are we all good today? I think we're good. Yes, we are. We're good. Obviously, it would be quite helpful at this point if I could just start off by teaching you all of astrophysics so you totally understood our universe. So that's what I'm going to do. So if we're all ready for that, we can get going. At this point, we discover the people who were dragged along here without quite knowing what they were coming to tonight. Who's this, an astrophysicist? Oh. All right, it's going to be fine. I've taught this to 10th graders and they get it, so we're going to be okay. Because it comes down to one concept. I want you to think about one concept, which is, there's a universe full of stuff out there. There's all sorts of forces pushing it around. And the things we see in the universe have to be in some sort of equilibrium. Those forces have to balance in some way, otherwise the thing will be unstable and it won't be around for very long. So if we look at, think of a ball on a hill, there's two places you could stick the ball where it won't go anywhere. It'll stay there, the forces will be in balance. But this one, obviously, is going to be unstable. A slight nudge one way or the other is going to send it rolling. So that's an unstable equilibrium. So what we want to do is look at what can we make out of the basic stuff of the universe and using the fundamental forces of nature around us, using those, what can I make that's stable? Okay, so let me introduce the four fundamental forces, the stuff that's going to push and pull things around. And I've thrown sort of two extra ones in at the bottom as a separate sort of conceptual category just to help us out here. But here they are, okay? This is the most busy slide text-wise, so we'll be fine. So gravity you're quite familiar with. Everyone here is stuck to the floor. No one is able to sort of levitate. That's gravity. We're all familiar with that. You are, however, not going straight through the floor because there is solid ground underneath you. That is ultimately the electromagnetism. There is stuff in the universe with charges. They hold together in atoms and all those sorts of things, which provide the ordinary solidness of the world around us. Inside of atoms, there are two forces that we don't really need too much of today, but I should tell you about the strong nuclear force, which holds nuclei together, and the weak nuclear force, which in certain circumstances can make nuclei fall apart. That's probably the last thing I'll say about the weak nuclear force, so we can all relax about that. The final two are they're actually some of the ones above in certain circumstances, but so thinking first about thermal pressure. So pressure, air pressure as we understand it, is simply molecules bouncing off things. That's all you need to know about air pressure. The air in this room bounces off the windows and pushes on the windows. If you put air in a balloon and then try and squash the balloon, you're pushing everything into a smaller volume, so it hits the sides more often, so it fights back against you. Voila, air pressure, okay? That's all we need to know about that. So ordinary matter, due to the fact it's moving, will resist being squished. The other thing we need to know about is what I've called there the Pauli exclusion principle, which is basically that at the very bottom level, the stuff that the universe is made of obeys what are called quantum laws. But basically the rules change. And all we need to know about that is quantum things really, really don't like being squished, even more than just ordinary thermal pressure. That is the beginner's class in quantum mechanics in one lecture. Those are our forces. All we're going to do now is just play them off against each other and see what we can make in the universe. So let me start with a non-astronomical example. Let's have a look at atoms. So I have fundamental particles that are charged, protons and electrons. There's also neutrons in the mix there. I can bind those together with the attraction those two feel, but I'll stabilize the whole thing by saying that actually it's a quantum system because these are single atoms, and so it won't like being squished. And hey presto, you can make atoms. So hopefully this is not causing too many flashbacks to high school chemistry for too many people. The electrons go around the outside, the protons are in the middle. Hopefully you remember all of that. The very nice thing about this is those orbits that are going around the outside have a very definite shape. And so if you bring two atoms together, you can make the electron go on a complicated orbit around the whole thing, which binds it together. And hey presto, that's chemistry in one sentence. So there's chemistry for you. Yeah, it turns out chemicals are quite good at doing this. They can in fact make DNA. That's the stuff you're made of at the bottom level. So there are 5 types of atoms there. The type of the atom is just how many protons there are in its nucleus. And thanks to the wonder of electrons wandering through different orbits, that whole thing holds together and is able to give the instructions for making a human being, which is pretty impressive from chemistry, to be honest. Okay? That's an example. So we just played off electromagnetism, one of the fundamental forces, versus that quantum nature, that things don't like being squished, and we made some atoms. The whole, the sort of key question in astrophysics is what's fighting gravity? You have an astrophysical thing, an astronomical something, when it's big enough that its own gravity matters. And if you want to make something stable, you better fight back against gravity because it's always attractive, it's always pushing down. So the different type of things we see in the universe are just different way that the universe holds things up against its own gravity. Or in some cases, fails to hold things up against its own gravity. If gravity is resisted by nothing at all, you have a black hole. Now, isn't strictly relevant to the talk tonight, but it's too cool to pass up. We believe there is a black hole at the center of our galaxy, and here's why. Okay? We live in a disk of stars, and we can find where roughly the center of it is. And if you point an optical telescope there, that sees like your eyes see, we don't see very much at all at that very center point where the star is. If you point a radio telescope, there is definitely something there that's putting out an awful lot of energy. What we can then do is, starting in 1995, is keep a very close eye on all the stars in its neighborhood. So these are all stars. They're not actually that big, that's just the blurriness of the telescope. And what happens next is this. That is a billion ton solar star. You know, it's a fusion reaction, and it's doing a complete U-turn in about a month. So there is something there with about a mass of 1 million suns in an extraordinarily small volume, right? Everything's turning around pretty darn quickly there. You think about the Earth's orbit around the sun takes a year. That's a month, and there's an awful lot of mass there. I'm going to play that again because it was cool. So that's why we think that there's a black hole at the center of our galaxy. Not strictly relevant to the talk, but I'd clearly love to talk about that more. I will force myself to go on. So that's black holes. What else can fight gravity? If it's atoms, the ordinary hardness of the stuff we see around us, then we get planets. Gravity is pushing in, and the ordinary hardness of matter is pushing out. So there's the usual suspects of our solar system. There is Earth, and there's the rest of them. Hopefully it makes you feel a little bit small. There's a limit on either side. If you have a very small rock, its own gravity doesn't really matter, so it could be any old shape. As you make a bigger and bigger rock, up to planet size, it needs to huddle itself into a sphere in order to really fight back against gravity, hence planets around. Okay? On the upper end, there's only so much hardness you get out of matter. So something that's big enough and ugly enough, ordinary hardness of stuff, ordinary sort of atomic forces won't cut it. So we need something else. And the thing that kicks in is that quantum, please don't squish me bro, hardness of matter there. So that's when you get something called a brown dwarf, which is a rather boring object. Here's an artist's impression. I don't know how they made this impression because we've never really seen one. But they're there in theory. If you make something a little bit more heavy than Jupiter, it won't hold itself up by its own atomic forces. You better have quantum mechanics kick in. The interesting bit is what you do next. You can hold up an object by thermal pressure. And when you have gravity versus thermal pressure, hey presto, you've got yourself a star. That's basically what a star is. It's so it's got obviously to have enough thermal pressure to hold up its own gravity for something that big, it's going to be really hot and it's going to glow, which means that there's light traveling throughout it, the light of the electromagnetism. When some of that reaches the surface, it will leak away, what we usually call sunlight. This star is constantly losing energy in that way, which is good because you've had unusually warm weather here, I hear, so that's been great lately. So we need something that's going to replace that energy, and that comes from the nuclear reactions at the centre, which is where the strong and the weak nuclear forces come into our story, and quickly disappear from our story. Here's a menagerie of stars. So, brace yourself for this. There's Earth. So what you need to do on each step here is shrink it down. Take Earth there and shrink it down to that point there and 2, and then there's the rest of the solar system. Take Jupiter and shrink it down to there. That's the Sun. Okay. Take Sirius and shrink it down to there, and then you'll get Aldebaran. Shrink that down to here, and we have even larger stars all the way out to Canis Majoris over on the end there. So you have a variety of stars. Now that might look like a wide variety of things. Actually, it's quite a narrow variety of things. If I told you how many atoms there were on average in a star and got one of the digits wrong, no one would really care, but the universe would care. Stars would care because of that balance. You can't just throw extra stuff in there without making a difference. If you're too small, there's too much stuff, then nuclear reactions won't fire up. It won't collapse and get hot enough for nuclear reactions to go up. You'll have a failed star, basically a brown dwarf. On the big end, it's not thermal pressure that's fighting back. It's now just the pressure from the light inside the star, and those sorts of things are unstable. So between 1/10 the size of the Sun, mass-wise, to about probably 300 times the mass of the Sun is that window for stars. Okay? One of the wonderful things about stars is that as they do various things for their life, they give us an opportunity to see them doing something quite pretty. Our Sun is burning hydrogen into helium. When it runs out of that, it's going to need to sort of compose itself, get its act together, and start burning helium into something heavier, carbon. As it's doing that, it'll undergo basically a fuel change, and that will look something like this. This is what's called a planetary nebula. It actually has nothing to do with planets, but it's particularly beautiful. It might look like this, it might look like that. I could do this all night. Yeah, these are planetary nebulae. You really do owe yourself a proper retina display and a properly dark room and Beethoven and some scotch and a lovely time just looking at these on the internet. Okay, I'll move on. How else can we hold things up against gravity? Well, that's the way that the Earth does it. We can just have planets in orbit. If you just keep on moving in a nice circular orbit, you won't fall into the Sun. We're moving at about 29 kilometers a second in order to achieve that feat, but it doesn't feel like that, so we're okay. You can move in other ways to avoid gravity. You can do it not through this orderly rotation in a nice circle. You can do it in a random fashion in what's called a globular cluster. This is a collection of stars. There's a lovely quote from Feynman down the bottom. If one cannot see gravitation acting here, he has no soul. Very interesting claim. What we think is going on here is, here's a simulation. This is just on a computer. So there is simply a swarm of stars. So any individual star will feel the attraction of everything here, but by the time it falls in, it's moving fast enough that it doesn't just stop there and be trapped. It goes out the other side, and the thing as a whole is fairly stable. Now you might wonder, will stars collide with each other? And it would be cool, but unfortunately it's not going to happen. Even in the very center there, the average sort of region around a typical star is comparable to a grain of sand in a football stadium. So unfortunately, stars aren't going to hit each other. It would look awesome. We can't do that. The same sort of dichotomy between orderly rotation versus this random motion we can see writ large in galaxies. So there's a gratuitous astronomical picture again. This is called the Pinwheel Galaxy. It is a spiral galaxy. You can see the spiral arms there, particularly beautiful form. If we could look at that from side on, now we can't, it's a bit hard to sort of wander around to the side of a galaxy. It might look like the Needle Galaxy. So these are thin disks of stars that are not collapsing because everything is rotating around. Okay? There is another type of galaxy out there which you may not have ever seen. It's called an elliptical galaxy. It looks like this, which has not an orderly rotation, but that random motion of stars in and out of the center, holding together just a basic, fairly featureless blob. So the reason why you probably haven't seen this is they never appear on, astronomy calendars. They're just not quite pretty enough. A great indication of this is this entertains me. This is called the Pinwheel Galaxy. This is called the Needle Galaxy. This is called NGC 1132. You couldn't even bother giving it a proper name. Okay. And so the final thing to ask is, okay, what's holding the whole universe up against collapsing in on itself? And the answer is that the universe is expanding. The universe is not actually an equilibrium system. It's not just sitting there. Everything is moving away from everything else. We see this in the galaxies in our night sky. Everything we can see is moving away from us, and in such a way that if we could put ourselves out on that galaxy over there, it would see everything moving away from it as well. So if you imagine sticking yourself here, you see everything move away if you're just on the surface of a sphere, but if you stick yourself on that one, well, everything's moving away from there as well. It looks the same everywhere. So, here it is. Behold, the Rosetta Stone, the cheat sheet of the universe. If any of you are thinking about doing a degree in astrophysics, I've just done it all for you there, so don't bother. What's fighting gravity? If it's nothing, black holes. Atoms, you get asteroids and planets. If it's quantum, please don't squish me, you get brown dwarfs. For stars, it's thermal pressure with some nuclear reactions to stop all that leaking away. For planetary systems and disk galaxies, it's rotation, and for globular clusters and elliptical galaxies, it's random motion, and for the universe as a whole, it's expansion. Now, all of that to say this. We know how to make stuff in the universe. We can do all of this, not just sort of hand-waving on a board, but in terms of equations. We can write down the equation for this force and that force, pair them up against each other and say how big does something need to be for thermal pressure to fight gravity, and then you get a rough idea of the size of a star. Once we've done that, we have an equation. And what's in that equation? Well, you find a few sort of pure numbers, like 2 and pi, that are also what are called the fundamental constants of nature. There are properties of our universe which we don't have any deeper explanation for. Things like how heavy is an electron, and how strong is electromagnetism, or how strong is gravity. We don't have a deeper explanation for why they are as they are, so when we hit those numbers, we've reached the end of the derivation. Now we go measure those numbers, put them in, and hey presto, astrophysics works, which is very nice. There's some really lovely papers if you don't mind the maths. Absolutely wonderful stuff. If you do mind the maths, then don't touch it. But this allows us to do something kind of interesting. We don't know why these numbers are what they are. We don't know why the electron is that heavy. We don't know why electromagnetism is that strong. So we could ask a question. What if they were different? And because we have the equation to describe that, we can answer that question in a systematic way. So we can take the masses of the fundamental particles, the strengths of the forces, and even the properties of the cosmos as a whole, and ask, what if these things were different? What we hope to answer is a question that's bothered physicists for a long time. These constants have got a lot of attention because they are sort of a sore thumb, just a glaring hole in our theories, just something we can't understand. So there's another quote from Feynman. It's going to be one in every physics talk, so I've got 2. All good theoretical physicists put this number, he's talking about the strength of electromagnetism here, up on their wall and worry about it. Immediately you would like to know where this number comes from. Nobody knows. It's one of the greatest mysteries of physics. A magic number that comes to us with no understanding. So, let me run through a few scenarios of what happens when we change these numbers. And the interesting question is going to be, do I get a different equilibrium? Do I just make bigger or smaller stars? Or do I lose that equilibrium? And so doing, ruin the universe. So let's go back to atoms. The basic properties of these things are their masses. So there's the mass of the electron, it's something we don't know. The proton and the neutron are actually not fundamental. They're made of smaller things called quarks. You'll either remember that tomorrow or you won't. We don't know their masses either. Those are two more fundamental properties of the universe. So here's what we're going to do. There's three numbers: mass of the electron, mass of what's called the up quark, and mass of the down quark. Not very imaginative names, but they'll do. There's three numbers. We can represent a choice of those three numbers by just a place in a block. Okay, so in a three-dimensional space, you need three numbers to specify a particular place. So we'll represent the possibilities as a point in this block. At the top, we've chopped it off at what's called the Planck mass, which is basically where our theories don't know what's going on. We don't know how to put together quantum mechanics and gravity, so up there, we don't know. So that's a good point to stop, because we wouldn't be able to answer what's going on up there anyway. And there's a sort of natural cutoff at the bottom, which I can describe to you in boring detail later on. There's 60 orders of magnitude there. To help us fit it all in, we're going to use what's called a logarithmic scale, which means that instead of going up in steps of 1, 2, 3, 4, 5, we go up in steps of factors of 10. So 1, 10, 100, 1,000, just to squish everything in. Okay? So here's your smorgasbord. If you're thinking of making a universe when you get home, I'll help you out by cutting off bits of the block here, which are a bad idea if you want to do anything interesting. So, for example, you want to avoid these sections here. Okay, avoid that bit there and avoid over the other side. Okay? Made a spinny movie of this. And I thought, yeah, that wasn't quite as good as I hoped it was. So we'll go back to this one. Okay, good. Here's why you want to avoid those. Over here, you don't get a proton. You get one of its larger brothers called the delta plus. It won't stick to anything. It won't stick to itself, and there is no other fundamental particle that it's going to stick to. So here's what chemistry looks like in that universe. There is one chemical element, which has the chemistry of hydrogen. That chemical element has one chemical reaction, which is hydrogen plus hydrogen makes hydrogen molecule. End of chemistry. That's the whole thing. That's all that ever happens in the universe. In our universe, there's an online database that you can go and look through if you are a chemist or a masochist, which has all the chemical compounds known in our universe, and there's 50 million of them last time I checked, and it just keeps on going up and up and up, right? 50 million here, 1. And over the other side, none. It has the chemistry of helium, so which is to say nothing at all. Helium doesn't have any chemistry. So avoid those bits at all costs. No, don't want that. I'll cut off a few more bits there. These are some more good things that you want to avoid. You want to avoid this because if you're not in that section, either your nucleus is going to eat an electron that tries to go around it. So see you later atoms, see you later chemistry, see you later periodic table. In that case, you don't even get any elements, because when that happens, you get a neutron, and so you get a universe full of neutrons, and that's the whole story. The other thing that you won't have if you don't stick into that section is that you won't have anything that has the chemistry of hydrogen. It's the other way around. You just sort of completely lose that one, so you don't have water or anything like that. You don't have fuel for stars. And there's also a region I cut out there where protons and neutrons won't stick to each other. So once again, see you later chemistry. These basic things are also the fuel for stars. So we've got to ask, all right, we need to fire some stars up at some point. So where will they happen? So we need to be in this section if you want stars to work. If you're at too low, what happens is anything big enough to burn is big enough to blow itself apart, which is probably a bad idea. And if you're not in that section, the first step that our universe does in any star is to take a proton and a proton, put together and make deuterium. If you are not in that section, that will be unstable. And so the first thing stars try to do, fail. And no star will ever get hot enough to actually, burn and produce the energy we need. And finally, if you're not in that section, stars in our universe have a fairly rare talent of being able to produce both oxygen and carbon. So as you sit here, as a carbon-based organism, breathing oxygen. You can be quite thankful for that little fact. Carbon is far and away the most versatile element in the periodic table. That's not just the fact that I like my own chemistry, that is just a basic fact of chemistry. You can make so much more stuff with carbon than anything else, it's unbelievable. So if you look across even just the first, take the first couple of rows of the periodic table and say, all right, take carbon and hydrogen, how many different ways can you put those together versus everything else? For carbon and hydrogen, it's like 29,000, and for everything else, it's like 50 maximum. Even silicon, which is supposedly a bit like carbon, it's only 55. The carbon is just the bee's knees. So let's make something. If you're not in there, carbon won't make, start that again. If you're not in that region, stars won't make both carbon and oxygen. It'll make one at the expense of the other. Okay? This is the fine-tuning of the universe for life. This is where we've been headed. This is the picture I want to sort of instill in your brain. So, as far as our theories are concerned, as far as the equations that we currently have are concerned, there is no reason to a priori expect why we would be in any particular part of this diagram rather than any other. Right? There's no theoretical reason to be here or there. We can understand what would happen in this universe just fine. The equations are fine. It's anyone who tried to live in that universe who'd be in trouble. But mathematically, everything's great. Okay? We are, of course, right there. And around us, there's a couple of universes that do interesting things and a whole host that do nothing interesting at all. And when I say fine-tuning for life, it's really fine-tuning for any kind of complexity. So if you need a rather too obvious visual metaphor here, there's the edge of a razor blade, if you need some help. By the way, this is, as you'll remember, a logarithmic plot. We're going up in factors of 10. If we plotted this on a sort of ordinary scale, a linear scale, in order to see that section there, we would need the height of the plot to be about 10 light years. So it's worse than I've got here. This is doing my best to show you how big it is by distorting the plot. But actually it's ridiculously small. So that's at the smallest level. Atoms, chemistry, the basic stuff of the universe. We can do the same sort of thing on large scales. We can look at how galaxies form. So, one of the things that I particularly enjoy doing is we can take a piece of the universe that's expanding and we can start it off with the initial conditions we see near the Big Bang. We see these in the cosmic microwave background. Basically, the universe is almost perfectly smooth, but not quite. There are slight lumps and bumps. There are slightly denser bits. As the universe expands, anything that's a bit more dense than average will collect matter from around it, and so the rich get richer. This is how structure grows in the universe. If you put all this into a computer, or about 5,000 computers, and run it for about a month and a half, this happens. Initially not very much, but as you'll start to see, the dense bits of the universe start getting bigger and bigger. The camera is rotating, the universe is not rotating, that's just the camera. So what we start to see is filaments and sheets of matter forming. At the very densest knots where lots of filaments come together, we get parts of the universe which can form galaxies and form stars and have stars blow up as supernovae, which feeds energy and stuff back out into the universe. So you can enjoy this pretty picture for a while. By the way, this is going fast forward at the rate of about 1 billion years every 2 seconds. So that's quite the fast forward. Okay? Obviously you don't want to do the history of the universe in real time. So just enjoy that. Okay. What I've been doing, which is a whole load of fun, is changing the rules. So there's one particular number that I'm interested in. What we discovered in 1998 was that the expansion of the universe is not just getting bigger, it's accelerating. A galaxy out there is not only moving away from us, it's moving away faster today than it was yesterday. Okay? Everything's not only getting away from us, it's trying to get away from us even faster still. So the most popular theory for why that happens is that there is a form of energy in the universe that is causing the expansion to accelerate. Now, you didn't really know what it was, so we called it dark energy. You can think of that as we're totally in the dark energy. That's all that joke deserved. Thank you very much. What we want to do is, what I want to do, what I have been doing, is changing the amount of dark energy in the universe. what that does, as you ramp it up, the universe starts this accelerating phase earlier. And so instead of this continual hierarchy where things are falling into everything else and continually forming more stars and more galaxies and bigger galaxies hierarchically, you reach a point earlier and earlier where things, instead of falling in, start getting dragged away. So it's not going to be as spectacular, but here's my little simulation. So here's just a little box that I did of basically no dark energy. Okay, and you can see stuff forming. What we can do is ramp up the amount of dark energy in the universe by a factor of 10. So this side is no dark energy. This is 10 times more than what we have in our universe. And what you'll see is they'll start off roughly the same. But as time goes on, maybe watch this bit here. Those two galaxies will collide. But on that side, they get drawn away by the expansion of the universe before they get together. They sort of miss that appointment. They miss the opportunity to join their gas together to make more stars. And the universe is a poorer place for it. If we really want to kick things up a notch, we can make it 100 times more dark energy. And the simulation on the right basically grinds to a complete halt. Gravity is unable to pull anything together to make anything bigger because it's all getting too far apart. We can zoom in. So here's that section I was looking at. We'll have two galaxies forming here that will coalesce into one giant galaxy. But over there, not much happens. We missed that opportunity. Kick things up by another factor of 10. And on that right-hand side, the dark energy is really shutting things down before anything interesting happens at all. So that's a factor of 100 larger. The problem is we can do a rough calculation of how large the amount of dark energy in our universe could be if it was something called vacuum energy. And it turns out that the possible range is 120 orders of magnitude. That's what happens after 2 orders of magnitude, right? So two factors of 10 instead of, I'm not going to count it out. Instead of a number with 120 digits in it, that's just 100. Okay? If we keep pushing it up, it's not going to take too many 4 powers of 10 before we start shutting down structure formation in the universe before it starts. And then the universe will literally make nothing at all. There will be no structure. You will have isolated protons floating in empty space for all eternity, and that is the end of the story of the universe. Depressingly boring. Okay? On the other hand, you only need, say, 10 digits before you get that, out of 120 digits. If you make it that large but a negative number, then you don't get this. The entire universe recollapses on itself in that amount of time, and you get, again, no structure because the universe just ends. This is called the fine-tuning of the cosmological constant, and it's such a great example because it's a very clear case of how to kill a universe. It's really a really great way to, I mean, if you're planning on being a supervillain at any point in your lifetime, this is a really great way to totally kill a universe because nothing ever is going to happen here. Nothing will touch anything else. You won't have life because nothing will interact with anything else. These are 2 examples that I've shared of what's called the fine-tuning of the universe for life. And if you would like some more examples, there's more in the book. So the strength of the forces needs to be in a fairly tight little regime. There's more cosmic numbers that better be just about right. The number of dimensions of space and time had better be 3 and 1, or else some pretty funky things happen. So if you want more information about that, it's in the book, which I wrote with Geraint Lewis. And now is the time to tell you that Geraint is an atheist. The interesting thing about this book is we wrote the first 7 chapters together, all the science and what fine-tuning means. We wrote all of that together, and there is literally 1 footnote which starts with, at this point, our heroic authors got into a brawl about whether photons from the thing. There was 1 point of disagreement, which you can go and find in the book at the back, if you like. The science is pretty much agreed on. Obviously, you never get total agreement in any area of science. But as much as you can, in this, it's pretty clear what's going on. If the universe had this particular value of the cosmological constant or the mass of the electron, this would happen. That's the standard thing that theoretical physicists do. So we can ask those questions and get an answer. So the science here is pretty clear. The question now is, what next? What do we do with it? So here's Geraint's favourite solution, which he defends in the book. It's called the multiverse. Basically what we need here is more cosmology. Don't know why Batman is involved. But he is. So for some reason, Infinite Crisis fight for the multiverse. Why you would have to fight for the multiverse? It's an awful lot bigger than Batman, but sure. So here's the idea. Basically, we won the cosmic lottery. Why did something unlikely happen? Well, we had lots of different goes at it. Why do people win the lottery? Because lots of people buy different tickets. We can only see one sort of telescope full of the universe, right? If light from some part of the universe hasn't reached here yet, we just can't see it because we can't see the light from over there. So there's only ever a finite chunk of the universe we see. So the idea is perhaps beyond what we can see, there are other universes where these laws, these numbers, these constants are different. That's the basic idea. Now, the way that you explain why we see this particular type of universe, which is fine-tuned, is because these are the only types of universe that have anyone in them to actually say, oh, I wonder why I'm in this universe, right? There's no one in the universe going, oh, I wonder why I'm in this totally dead universe. There's no one there, right? This is one of the interesting things about cosmology, is that at some level you are always modeling yourself, whether you know it or not. You are modeling a system that you are in, always. So, why would we think that the multiverse is a serious idea? There are some theories about the very early universe which suggest that that this sort of global picture of different bits of the universe having different laws might fall naturally out of a theory that we had anyway, called cosmic inflation. If the universe in its early stages had an exponential expansion, exponential expansion, in its very early stages, that would explain a few things about the universe. What a lot of inflationary theorists have tried to defend is that this will naturally create a sort of bubble-like structure. There will be inflating bits of the universe in between, but every now and then part of the universe will stop inflating and have what we would call the Big Bang. And hey presto, you've got a universe, and if you manage to scramble up the initial conditions there, you'll have yourself a multiverse. Now, that's a bit speculative, but perhaps surprisingly, there is a way to test this idea. And if you thought this talk was weird so far, then yeah, here we go. Boltzmann brains. Revenge of the Boltzmann brains. Here we go. If you have a multiverse theory, you have an idea about the kinds of universes that might be out there. What you are really predicting is a population of things of which our universe is one member. And what you want to ask yourself is, are we at least typical of the life that we would find in that universe? So think about sort of in your head, going around to all the different universes in the multiverse with your clipboard and your pen. If the universe is dead, there won't be anyone to talk to. But if you find someone in your universe, say, all right, what is your universe like? And if 99.999% of the universe, the people you survey said, it's about 40 feet across, it's a bit cramped in here, and only one in a bazillion says, oh, I can see like 40 billion light years away. That idea has made a wrong prediction. Now, what we would love to do with any scientific theory is to see, directly evidence for it. Unfortunately, we're never going to be able to do that with the multiverse because, by definition, all these other universes are elsewhere. But there is a way to fail that particular test. And one of the really interesting ways is the way that we got here was via that entire history of the universe. You start off with smooth conditions, gravity makes galaxies, galaxies make stars, stars blow up, that stuff collects in planets, planets go around for ages, ask a biologist, and then somehow life forms and life evolves, and then here we are. That's a really long process, which requires a lot of order there from the start for all that to unfurl. You might run into a problem in your multiverse which you hadn't expected if it's easier to avoid all of that and have the universe just create a brain, a single brain, with memories in it already that make you think that you're in this room. So if you went around with a clipboard to everyone who thinks they're in this room and said, all right, where are you? Oh, I'm giving a talk. It might be the case that actually most of those are isolated brains who are kidding themselves. They're just fluctuated out of whatever happened in the Big Bang, and they're shortly going to go. They're just kidding themselves. So this is called the Boltzmann brain problem. It's weird. The reason why it's a problem is because it could infect your theory. The problem is not that how do we know we're not Boltzmann brains? Okay, we can take that problem and just ship it off to the philosophers and have them talk about that for a while, radical skepticism and all that. This is a different problem. This is about a theory making a prediction. If a theory says that the most likely way to get an observer is to just pop one out of nowhere, pop one out of the Big Bang all in one piece and have it stick around for a few seconds, it's made a wrong prediction because that's not what we see. It's a pretty weird idea, but the multiverse is a weird idea, so we're going to test it in weird ways anyway. Finally, one of the reasons why this whole field has sort of such an interesting lay following, I notice we're in a theological seminary, is because it, to a lot of people, suggests a fine tuner. The way I love to think about this is imagine a collection of chess pieces on the board trying to do the science of their little universe. They watch the other pieces move around, they try to work out what the rules of chess are. Suppose one day, after watching all the bishops move diagonally and think, okay, bishops move diagonally, that's a law of nature. If they keep watching for even longer, they'll see castling. At some point, one of them writes down the laws of chess, and it's finished. They're totally done. They've worked out their little universe. Okay? Would they still have questions about what's going on? And in particular, the questions we've been asking, what if things were different? Those little chess pieces could ask, okay, why aren't we playing checkers? And if you want to answer that question, you're not going to get it from the laws of chess, right? Bishops move diagonally is not going to tell you why you're not playing checkers. You need, if there's an answer to that at all, it's going to have to come from a level above. So imagine that at some future meeting of the very important Physicist Association, Alberta Einstein, distant great-grandchild of Albert, walks up to the blackboard and writes down some equations, draws some diagrams, and theoretical physics is over. We've done it. We've actually written down the ultimate laws of our universe. Imagine that happened. Okay? Massive round of applause. Applause dies down. A room full of physicists stares at a blackboard full of equations. What now? What do we do now? Let's let physics, let's let science have everything it wants at the sort of bottom level. Right? Answer all the questions. Get the ultimate laws of nature, everything you possibly want. Okay? What next? Are we done? Would we be happy to just go, all right, yeah, we're done, that's it, let's just high five and go to the pub? Or would we have more questions? I mean, there'd be more physics to do in working out how those laws played out. But if you want a deeper answer, if you start asking questions like why those laws rather than some other laws, you're not going to find the answer on the board. So where are you going to look? So the way that the fine-tuning argument works, the argument for the existence of God, I think works a bit like this. What we would like from an explanation, I think, is that it takes a big set of possibilities and really cuts them down. You do a lot of explaining by not being sort of vague, by really being really specific about what sort of thing you would expect if your idea was true. So here's an illustration of really cutting down the possibilities. Does everyone know Guess Who? We had this issue in Indiana. Okay. For those who don't know, the idea of this game, and I'm going to explain Guess Who to you, this is awesome. You and your opponent will pick one of these characters each, and then by a series of questions, you have to try and work out who your opponent has before they work out who you've got. So if you ask a really insightful question like, a pretty risky question to be honest, like does your person have both a beard and a mustache, and they say yes, you really knock down the possibilities. Because it's Richard, that's the only one, okay? This is obviously a memory of me as a kid, losing a game catastrophically, okay? If you ask if you just don't have any information at all, you just have to guess out of those possibilities. If you ask a really boring question like, is it a small child? Well, there is one, sorry. One goes down, but that's not really particularly helpful. So here's what I want to say. When we get to that point, just imagine getting to that point. Let's let physics do everything it wants to do. Let's get to that blackboard. And we say, all right, are there other ways the universe could have been? And why is it this way rather than some other way? Could the universe have been different? And the answer to that is pretty obviously yes, if you're a theoretical physicist. This is why theoretical physics is so hard. Because every mathematical possibility is just another way the universe could have been. right? Unless you write down something mathematically inconsistent, the whole of every mathematics library is at your disposal. So next to Alberta's board, we could write down, you could fill board after board after board with other equations, other mathematical structures, with other numbers, or other equations, mathematical stuff we haven't even thought of. And right there in the middle would be Alberta's, and there would be nothing about that board that screams at us, hey, that's the one that actually describes reality. Right? Scientific laws do not predict their own success. There's nothing in the maths itself that says, I'm an equation, I demand a universe that is described by me. That's not the way they work. They describe a universe that's out there. So if you want to say why that particular one rather than all the other ones, you're going to have to look for a deeper explanation. If you are what's called a naturalist or a materialist, and you think that the ultimate laws of nature are just the end of it, if you think physical stuff is the only stuff, then you're done. That's it. You just have the entire smorgasbord of guess who things up, and you can't touch them. There's just all those possibilities. You just accept that that's the one that describes reality, and that's it. That's all you can possibly say. What fine-tuning shows us, I think, is that when theism steps up to this board, it has an awful lot to say. If you get the clue, get the hint, that the universe that actually exists is one that permits the existence of creatures who can experience good, experience love, have morally meaningful lives, you get an enormous clue about which universe is real. Think about some section of these possibilities, which represent all the different values of the cosmological constants, say. There's all those possibilities. If you say, all right, we have the clue, we think possibly that the universe is the kind of place that will permit interesting structures that could have morally significant lives. Suddenly, like, the ultimate guess who, all those other universes go down. And you've got a great explanation. You really do understand something about why the ultimate laws of nature are the way that they are. That, I think, is how the argument runs. Now, obviously, Geraint disagrees. And she would like to hear us, read us for a chapter going back and forwards about all of this stuff, and the book is up the back. So I think there's an interesting sort of lesson here, just thinking more deeply about what the laws of nature are on theism. I like to think of it as sort of like the relationship, so the laws of nature and the constants of nature and the way the universe plays out are a bit like the characters and the plot of a book, and the way the story starts is sort of the initial conditions of the universe. And we can do all of that, and we can discover new chapters in the book and new characters and new relationships between the characters. But at some point, we might want to ask, who wrote this thing? And if you can explain a lot about the book via that sort of explanation, then you've really got something. And in particular, no character in the book is going to replace the author. Science can do all it likes, can discover all the characters in the book as much as it likes. It won't replace the author because it's just a different layer of explanation. If naturalism is right, putting this the other way around, then it's not that something in the universe replaced God, it's just that the universe didn't need that at all. It's not that we found something in the universe, Harry Potter could suddenly replace J.K. Rowling, or put in your favourite literary reference there at that point. So I think that's a lesson here that's interesting to think about, so that science, when it gets to the end, when it's staring down that blackboard, if you want your questions about why that blackboard, why this universe, and if you want to go for the big one, why anything at all, I think theism has a lot to offer as an explanation of those things. So thank you very much.
So now we'll take about 40 minutes of questions. Joel, you can start us, and then just you can line up there, and
I can begin now.
you can begin now.
Okay. During the lecture, you alluded to dark energy as the mechanism governing the expansion for the universe. In the spirit of fine-tuning, I was curious. So if you took the standard model of the universe and you started toying with it by adding auxiliary particles, which are very weakly coupled to the particles that we can observe, in the sense that on the energy scales we can probe empirically, they would be effectively invisible to us, except for the gravitational effects, which we would feel because gravity acts democratically. Right? Would you be able to replicate, Could you conceive of some kind of physical model like this where you could replicate effects that are qualitatively similar to that of the acceleration of the universe, even if you couldn't get the numerics exact?
So you basically just described dark matter.
Yes, I wanted to know, can you take the Lagrangian of the standard model, start adding in fields, start actually tweaking
right.
it, and then have these and then do
Yeah.
some simulation where you put in these particles all over the place, and you're able to make the universe expand in a manner similar to that which we observed.
So basic vanilla flavored dark energy, what's doing this thing is you basically say there's an energy attached to any given volume of space.
Yes.
And you can make more interesting, flavorful models by adding an extra.
That are weakly coupled to that which we observed.
So particles in and of themselves act like matter. They cause the expansion of the universe to decelerate. It's that vacuum energy, the energy that's there even when there's no particles, that makes the expansion accelerate. Unless you can invent, and I'm sure you, clever chap, probably could, some interesting new way of doing that. But the standard, the ordinary, field, it doesn't really matter how strongly they're coupled to each other because it's gravity that matters. If they act like ordinary matter as far as gravity is concerned, they'll make the expansion decelerate rather than accelerate. Which is why it's a bit like, imagine you only knew of gases that were heavier than air. And then one day you saw a helium balloon going up into the, like, what on earth is in that thing? We see the universe doing something that no known form of energy can do.
I suppose one point where I'm puzzled is I thought that energy only mattered relative to the vacuum. Although there are various effects you can disturb the vacuum energy, like the Kessner effect, but I thought in general the vacuum energy even has to be sort of formally set to zero.
Oh, in particle physics, the absolute value of the energy in the vacuum doesn't matter. It's only the differences.
Yes.
But in general relativity, it sees the vacuum. Which is why actually particle physics probably won't solve this problem in and of itself, because it doesn't really know what it's doing to the expansion of the universe. It's totally blind to all of that.
Is this on?
Yes.
So I wanted to ask you to think about temporal dimension. As we understand this evolutionary theory, it took a long time to get to the point where we've got enough recycled heavy elements to form planets like the Earth and let life evolve. So we're some 13 billion years out from get-go.
Yep.
But then again, how long can the proton last? I've heard something in the order of 10 to the 50 something.
Yeah.
Right. There's an outer limit of proton decay. Now, how long can the longest stars last? Well, they're in the order of 10 trillion years or so. Then there's a question of, what's happening to galaxies now? Right. So galaxies now, are we sort of post-peak and on the downward slope in terms of the formation of stars?
Yes,
And,
yes we are.
well, maybe, right? Or it could be, since we're getting sort of the collapse of galaxies coming together in gravitationally bound groups, and then the explosion between those gravitationally unbound groups, right? So one of the things we do know about galaxy formation is that as the galaxies fall in, they tend to create these sort of stirred up red and dead spheroids.
Yeah.
Right? So that implies really that we are, but the long-term prospect there's still a little up there. But here's the point, with all that, it looks like there's a reasonably short window. Again, you're going to do it in sort of a logarithmic scale.
Yeah.
Right? So you've got nothing, and then here's the scale from the beginning of the universe to the decay of the proton. We're here.
Yeah.
The minute where life might exist,
Yeah.
and then the rest of them dead. So what does that imply for the fine-tuning?
Okay, so there are ways we could imagine packing more life into this universe. That's interesting, and if you think, it would come into this if you thought that, take the multiverse as an example. If you thought that the most likely universe was one where everyone was just packed in cheek by jowl, just life as huddled in as you can get. But really, in terms of the bigger picture of what's happening over the vast swathes of parameter space, what's happening in all these possibilities, most of them go from dead to dead without going through life in between. That's the sort of the headline story here. But it is interesting that in this universe there is it's not open-ended. There is that finite window for where you'll probably get life to form, and not much outside of that. one of the interesting things, it's also a very good window for learning about the universe. If you're there too late, the expansion sort of pushed every galaxy out beyond your telescope reach, and extragalactic astronomy gets really boring because there's just nothing to see beyond our universe. So, I think it's a sort of secondary effect. I think the headline here is that dead-to-dead universes are the main thing, but it could affect. So for example, if you're thinking through the argument for theism, and you thought, well, actually, God would want to just put lots of life everywhere. This universe isn't one of those. How strongly do you think that that's what God would want to do? And if you don't think so, then you've got an argument against it.
I'm curious in terms of your own modeling, if you think there are any alternate universes where life might extend for a much larger part of that temporal span.
Yeah, well, it's hard to do. So even in a universe with no cosmological constant, where you don't get sort of death by accelerated expansion, we've just run these simulations actually. The star formation still dies off. You stop making stars, those stars burn out. You'll still get all of those sorts of effects. You might get a very rare event making a few more things, but it's actually quite hard to make a universe which is obviously more packed than this one. But you kind of end up ruining things in entertaining ways. So I often hear people say, what about the vacuum of space? All right, well, why don't we just go ahead and fill the whole solar system with breathable air? Fantastic. We're going to plunge into the sun in a month. Sorry, friction, another entertaining way to ruin the universe. So yeah, there's interesting questions there.
Let's use the microphone. If you don't want to,
I can repeat the.
We're going to try to record this.
I believe that cosmologists, and I think you were saying this also, talking about the expansion of the universe and saying that the farthest galaxies are accelerating the greatest. Is that correct so far, more or less?
Well, yeah. No, well, the rate. So there's issues of look back time. You look back into the universe, you're looking back into the past, and actually the universe wasn't accelerating in the past.
Well, that's exactly the point. That at least in the conventional understanding, if the image is given of a balloon with blown up and everything, and so everything's moving away, and the parts on the balloon are all moving away equally, but at an expanding rate or accelerating rate. And again, that's the puzzle to me, that the farthest away galaxies, the reason in the first place we say that they're accelerating away is because we analyze the light coming from them.
Yep.
And as you just indicated, the farthest away, it takes the longest amount of time. So in effect, in one sense, we're looking into the past. So if we're looking into the past, we might be looking 25 billion years into the past, assuming that's the radius.
It's before the Big Bang, sorry.
And
It's about
if we're
3.
looking that far into the past, then it's not happening now. So we wouldn't know that the universe is expanding now because the time it takes the light to reach us from those purportedly expanding or accelerating universes is maybe 25 billion years in the past.
So there's a sweet spot in the middle. So when the universe was about 2.5 times smaller than it is today, so a couple of billion years ago, there's a sweet spot where you're far enough away that you can see a lot of the effects of the expansion, and you see the light will travel for long enough during the accelerating phase that you'll see the imprint on the light. There is a sweet spot there. So you're right, if you go too far back into the past, you won't see evidence of the acceleration in and of the thing itself. But as the light travels across, it travels through all of that time, including traveling through the accelerating phase, and that leaves an imprint on the way, the relationship between how the light from the star is dimmed by the expansion and how it is shifted in wavelength.
But final point, so nonetheless, I know it's very difficult to talk about what's happening now in terms of the whole universe.
Yeah.
But to say that the universe is expanding now has
Yeah.
to be rather theoretical, since it would take so much time.
Oh, sure. Yeah. So we only ever see what's called the past light cone. You only ever see, as you look out, you look backwards in time. So yeah, maybe the rest of the universe all decided today that it wasn't doing any of this nonsense anymore and stopped. We wouldn't know until the light from those regions got to us. So there is absolutely an extrapolation there, but we're doing cosmology. Of course there's going to be an extrapolation. The best we can do is try to account for all the data that we have. We, back in the 1920s, made the ridiculously simple assumption that the universe is the same everywhere and expanding uniformly, like the picture of the balloon. That's a ridiculously simple assumption that we've been getting away with for the last 100 years, and no data has overthrown that model.
Just to clarify my own understanding, final point, the belief is that initially there was a deceleration.
Yes.
From the Big Bang, and then a sudden acceleration.
Yes.
Okay, so that
Not sudden, it's gradual. It slowly transitions from one to the other.
so that doesn't preclude, it seems to me, the logical possibility that it's decelerating once again.
Sure, yeah. It just needs something that's going to do that. Okay? So yeah, if you want a model that'll do that, you need to tell us what's the universe made of. If you're using Einstein's equations, show us how that's going to happen, and then show us whether that accounts for the data. Just keep doing cosmology.
Hello.
Yeah.
So I was looking at arguments for and against fine-tuning, and one of the arguments against fine-tuning involves the multiverse, and involves something that people call a multiverse generator. And what people say to argue against such a multiverse generator is that also needs to be finely tuned. And I couldn't understand why such a thing would also need to be finely tuned. If you've ever heard this argument,
Yeah.
why would that also need to be finely tuned?
So in any sort of, if your idea about the multiverse, each different universe is a separate postulate in your theory, then you're going to have real trouble with Occam's razor, because you're making an awfully not simple theory. But if you can make a universe generator and just crank the handle and out come all these different universes, then you've actually got something simple that's generating the variation that you need. But I mean, there are ways that the universe generator can fail. So the question is, okay, there must be some, for this to be a simple hypothesis, there must be some sort of law, some sort of regularity that's governing that generator. Does that physics itself need to be fine-tuned? And maybe we get to the point in cosmology where maybe there is a multiverse and it's sort of it's safe in its own skin. It naturally produces universes like ours, and we're typical in all of that. So we have a sort of a successful theory. But when we go and look out beyond, put that physics on Alberta's chalkboard, okay? We've still got all the other ways around it that the universe could have been. And so we've still got potentially a big open question and the possibility of an explanation in terms of a deeper reason.
Okay, Alex is going to ask a question, and then catch my eye and wave your hand at me so I know who else wants to ask questions. So, is that you?
Okay, look, I'd like to hear a little more about what you meant by structure. So you said in these certain regions you're not going to get any structure. I mean, you might think, well, so structure is something like, how many bits of information do we need to describe?
Right.
But then at any two-particle system, it's going to be describable by a countably infinite number of bits of information if you look at the distance between the particles.
Right.
And a countably infinite number of particle universe is also going to be describable by the same number of bits.
Right.
So what is this structure that some of these universes have that others don't?
Okay, so when we try and do galaxy formation in our universe, it's a complicated problem because lots of structure form. So the universe, it's called going non-linear. So there's how much detail do I want to bore you with at this time of the evening? Basically, in our universe, because so much structure forms, it's a complicated problem. As you start to ramp up the cosmological constant, it's now a much easier problem where you say, what is the distribution of matter in the universe? And that is actually a remarkably easy thing to calculate once you've totally sort of ruined the universe with dark energy. Sorry, I sometimes call it cosmological constant, roughly the same thing. So by structure, all we really mean is, take any definition of life that you like. These universes are really simple. They're almost perfectly uniform. So pick any definition of life that you like. Will there be life in that universe? And because they're so simple, we can pretty confidently say no. It'll be a very sparse gas of particles that occasionally bounce off each other, but because of the expansion of the universe, it might happen every trillion years, and then after that, a trillion years. So by any lights, I think, life, you wouldn't describe, would you like to go and live in that universe? Probably not. Would you expect anything to, be able to answer your questionnaire in that universe? Almost certainly not. So I wouldn't cash structure out in terms of information theory, because you run into those sorts of ideas. But I think just in terms of anything that you would call life, anything that you would call complexity, I think we can fairly safely say, because these universes are so simple to describe, that nothing like that happens in those universes.
I mean, I'm just thinking, you could have an isomorphism between the phase spaces, so as long as the phase spaces have the same cardinality, so you should be able to find isomorphs of light, even that universe with the two particles. It's just the same complexities, all in the fine digits in the distance or something.
Oh, okay. Sounds like a question for you tomorrow night.
It's a very different kind of complexity from the kind of complexity we've got here, but if the
Okay.
states in the phase space is the same, then they're isomorphic.
If you think there's a physical minimum to make, say, a conscious agent, maybe you don't, but then I think the sort of playing with infinities in phase space won't give you that. You need a certain amount of complexity in a physical system for it to do, to do a calculation. You're going to come back with that isomorphism again. Yeah, it's a good question. I'm not totally sure.
Well, I guess here I was thinking cardinality is not much of an isomorphism.
Try really hard to make this at a certain level, and everyone just kicks it up a notch.
Bidirectionally deterministic.
Okay.
Then at least you can match the trajectory. You can have a bidirection. You can have trajectories at least.
I have maybe a different kind of question.
Yep.
Where I get stuck is in the idea of putting together a counterfactual probability space.
Right.
And then saying, isn't it amazing that we are located in a certain spot in that
Right.
space? Let's say somebody programmed a computer
Mm-hmm.
out of my sight, and it ran a simple program, and it produced an output. Let's say 10 bits.
Mm-hmm.
It calculated something. And then that message is sent to me, and I get 10 bits. And I look at those 10 bits, they tell me something,
Mm-hmm.
and then I start wondering, well, there are 2 to the 10th possibilities here. How come I got these 10 bits?
Right.
This is where I get stuck.
Okay.
Because I question the validity of setting up that probability space.
Right.
Since it's completely counterfactual.
Okay. So I think there's a couple of things to say there. I think we apply that sort of reasoning in all sorts of things and do it successfully. If I see a deck of cards on a table and they're all totally in order, I will presume that someone put them in order. If I see them in what looks like if I throw them on the ground, kick them around a bit, then pick them up and put them in, the probability of that arrangement is the same as the probability of the other one. But I don't think now I have something worth explaining. So a low probability is not enough, I think is what you might be saying. So 10 bits of information, who cares? But there must be some circumstances in which you see something looks improbable and you think, hang on a minute, I've got a way of explaining that which will make it seem less improbable. So if I if we're playing poker and you get a certain set of 5 hands, maybe you get a pair and another pair a couple of turns later, you might not think there's anything to explain. But if Bob, who's playing next to you, is getting royal flush after royal flush, there's improbability there is the same. But now you think, okay, I could explain what's going on over there if I think that Bob is cheating. So I think the way this works is, but that again, that's sort of you might think of that's a counterfactual, but it's an example in which we sort of naturally reason in those terms. So I think the question here is, there's an improbability here. Is it the sort of thing that suggests an explanation, or is it the sort of thing that I can just leave as an unlikely event? So it is possible. What naturalism will say is that no, this is just one of those things, right? We've reached the bottom level. That's it. We're done. I think what the theist is going to say is, no, we've got an explanation here that could actually do some work for us. Let's explore that and see whether we find it useful. It might turn out to be deficient in other ways, but that's something worth thinking about.
Anyone else?
Thanks. So I hesitate to ask this question in a room with a bunch of mathematicians, but so you have the region with, when you sort of cut down the region of the possible world where you had the, I think it was the order of magnitude up to 60 in your diagram, and it kept getting smaller and smaller.
Yeah.
And you kind of made this comparative judgment about how the size of that, the life permitting worlds or the complex structure permitting worlds versus the ones that don't.
Yeah.
But isn't there an infinite number of worlds within that region?
Yes. Yeah.
So how do you sort of deal with the infinity as a much smaller region than infinity?
Right.
So the infinity outside that, infinity inside that.
So the first thing I see is that there can't be a in principle problem here, because we need to do this when we test any kind of theory. So if you have any kind of theory with a free parameter in it, with a number that you just have to stick in, you need to be able to say, all right, what would happen if there were different values? And do I think this is a good explanation, a good theory? I have to be able to sort of average over all those possibilities. And so that's the same sort of problem. If we can't do that, then there's a whole host of scientific theories that have to go in the bin because we can't possibly test them. So I think the answer to that is we can justify what's called a measure. And in this case, it's a measure of, I'm a card-carrying Bayesian. The probabilities measure our state, something about our state of knowledge. It's how does one particular fact support another fact. So if I see blue skies outside, how much does that support the idea it's not going to rain this afternoon? I can think about those two. It's not an implication, but within that, I can honestly represent my state of knowledge about which part of this diagram I would expect to be in, using just the ordinary stuff of probability theories, how we deal with infinities anyway. We just put a measure over sets, basically. So we have the apparatus to do that. You just need to be able to justify it. And I think the justification comes in terms of these degrees of belief that you get from sort of modern probability theory. Does that answer your question? You might want to also ask Alex.
Well, I have one question and then might ask another after, depending on the outcome. So when you talk about what we can observe, of course you can't observe outside of the light cone, you get into trouble with relativity.
Yep.
Do we believe that the universe is actually much vaster than that which we can see? Or do we believe that we can more or less see everything and we know how vast it is?
We have no idea.
We have no idea.
So there is a way, if the universe turned out to be finite, that would imprint on our observations of the cosmic microwave background. We've not seen that. The universe has to be bigger.
Many orders of magnitude bigger.
Oh yeah,
Okay,
infinitely
so,
bigger.
because I was thinking of this in light of the comment you made during inflation, you could have isolated pockets,
Mm-hmm.
and then you could have something like, you could apply anthropic arguments without having a multiverse. Is that correct?
You need the constants to change from place to place. You won't explain the lottery if everyone writes down the same numbers.
Well, that's what I was about to ask. I was about to ask if there were any mechanisms one could conceive of, any theoretical mechanisms where maybe you could have some slowly varying parameters. Well, for example, So I know in string theory, by compactifying, by curling up dimensions, you can build all sorts of different models on what we can observe. If you had the geometry, this is not a, I haven't studied the compactifications carefully, but I don't know if you could vary the geometry and get the parameters to vary. But if you could hypothetically get the parameters to vary very, very, very slowly, and you had a universe that was very, very, very big, could you have some kind of anthropic argument that would apply to the universe? And you wouldn't need to appeal to the multiverse.
I think that would essentially be a multiverse, except that when you zoomed out, if you wanted to, it'd be hard to draw lines around this universe, that universe,
Well,
but if you
it
say...
It would be an effective multiverse.
Yeah.
But what I mean is they would all be part of the same geometry.
Sure, yeah. So there's no... you run out of words to say, well, you've got universe, sub-universe, what are the bits of the multiverse called? Is there a sharp line between them, or is there a smooth transition? I don't think that really matters for the argument. So you just need different bits of the universe to have different conditions, such that at some point, somewhere, life will turn up.
Okay. Good. When I thought of multiverse, I was thinking of completely disjoint.
Yeah.
I guess space like separate.
Yeah. Probability-wise, you just need variation.
Okay. Thanks.
Okay, and I guess one more question.
I've heard people object to the fine-tuning argument based on analysis of deeper laws, basically saying, well, there must be some kind of deeper law that makes things have to be this way. And as soon as we understand that, then we'll understand the fine-tuning mystery will solve. But isn't that always just pushing the problem one step further back?
Possibly. If we're thinking in terms of, staring at Alberta's blackboard, there might not be any constants on that board, right? But there are still other ways the universe could be. What fine-tuning gives us is a sort of systematic way to look through a set of possibilities. If we had laws with no constants in them, there wouldn't be that way of looking through the possibilities, but there would still be a whole set of other possibilities out there. We might lose the ability to sort of be as systematic as we would like to be about this fraction versus that fraction, and all those sorts of things. But I think the same sorts of worries would be there. In fact, this is one of the things in Chapter 8 that Geraint and I agree about. So we start off thinking about this exact issue and come to that conclusion that we'd still have something there to explain, even if there were no free parameters, no constants.
Okay, let's thank Luke.
Thank you very much. Wait, nobody move. Wait, nobody move. I promised Geraint that I would take photos of, yep.